Hello everyone, welcome to another Watch Me Do Math video. This video is it's a bit of a joke, honestly, but this topic came up in a conversation I was having with some friends on the idea of fan shipping, and we realized it would probably be a good maths question. So I'm going to endeavor to answer the question I've set out in front of you. How many possible BTS, or for that purpose, n-member band, i.e. a band with n people involved, fanship configurations are there? So what do I mean by a fanship configuration? Well, there are a couple of ways to look at it. One is if you have constructed some kind of fantasy in your head where particular people in the band like other particular people, but that's a different case to one I'm thinking of, which is essentially you pair up people within a band to go off and be couples of some kind. Now, honestly, I'm really not that, I'm really not a K-pop fan, and I think the practice of fan shipping is a bit creepy and disrespectful because, they're their own people, right? They can try to have their own lives without, rabid fans interfering in them. And there are also other reasons why I don't really like the K-pop industry in general, but nevertheless, this is a math video, and the problem posed is interesting. So we're going to take a look at it from a mathematical perspective. Firstly, with this example of BTS, which is very famous, having 7 members, and also interesting mathematically because for odd numbers this problem is slightly harder. And then we're going to try and generalize the approach we take to answering this question to any sort of group of people with n members if you want to find a solution to this question, like how many fanship configurations are there. So, if you're not familiar with the band BTS, it's just a group of 7 people. For simplicity's sake, I'm just going to call them 1, 2, 3, 4, 5, 6, 7. Or boy 1, 2, 3, 4, 5, 6, 7. And the question we're asking is essentially, in the latter case of the 2 that I described, how many ways can we pair or not pair them up such that we create one sort of fictional configuration of how they are somehow in a romantic relationship? So for instance, this would be one configuration. Nobody's paired up with one another. Another configuration could be members 1 and 2 are paired up. No one else is paired up. Another configuration could be 1 is not paired up, 2 and 3 are, 4 and 5 are, 6 and 7 are. And the underlying rules that describe the ways in which we can pair these people off is that firstly, pairs must be exclusive, as in if once you have constructed a pair of which 2 members are apart, neither of those members can be in a pair with any other members. And secondly, pairs are, you can reorder pairs, and that's not a different configuration. For instance, 1, 3, 2, 4, 5, 7, 6. This is equal to the configuration above because the pair of 3 and 2, it's a pairing. It doesn't matter which way you say it. You're just describing 2 objects that are somehow linked. Well, I say objects, they're human beings, but this is mathematics. I'm making abstractions and generalizations. So, what approach can we use to this problem? The first thing you want to do in a mathematics problem, especially a fairly abstract one, like things to do with counting, is trying to figure out an approach you'd use for the simplest case. And I thought the simplest case would be for an even number of people, taking everyone to be paired off. So essentially sorting 6 people into 3 pairs. How might we go about that? Because 7 people, you always have one person left out, or some odd number of people left out, and I believe that might add a degree of complication to the situation. So we're going to try this with the idealized case of 6 people first. So one approach that I thought it might be appropriate to use is the approach of ordering them into sort of slots or positions in a line, and then setting up dividers every 2 spaces and just declaring that whoever is in these two spaces are a pair, whoever's in these two spaces are a pair, and whoever's in these two spaces are a pair. So first, we want to find out how many ways can we arrange these 6 people in a line such that every order or arrangement of these people in the line is different. And I'm just going to write that like this, which I'll explain later. Then we want to correct for the fact that whether you have person 5 then person 6 or person 6 then person 5, if there are objects A and B in any particular pair, doesn't matter if they are BA. So for each pair we can divide by a factor of 2. So I'm just going to write it like this. I'm writing this mathematical terminology down so I don't forget that each of these is one component of the solution. And finally, I want to account for the fact that if you have pairs that are different overall sequences, but the same sort of combinations of pairs, such as 1, 2, 3, 4, 5, 6, or 3, 4, 1, 2, 5, 6, I want to make sure that we're not double counting these. I need to find the number of ways this ordering could be re-expressed in the overall order of 6 people, and divide by that to make sure that we're only counting a possibility like this once. So again, I write that there just to remind myself of what we're going to do. So if I clear all this, I'm going to start with this n exclamation mark. So if you're not familiar with this exclamation mark in mathematics, it's pronounced factorial, as in this expression is n factorial, and physically speaking, it's the number of ways you can order n objects in a line, the number of unique orders or arrangements that you can have for those n objects. And mathematically speaking, well, if n is an integer because it's a number of objects, like I'm sure this function has some more abstract definition for n that is not integer, but for n being an integer, it's mathematically equal to n times n minus 1 times n minus 2. But there's really no point in me telling you this. Like, you multiply by the numbers down from it, down from it, down from it, until you get to 1, like 3 and 2 and 1. But it's not helpful for me to tell you this mathematically, but it's more helpful if I can show you why this is the case. So if you have n slots in which you're going to organize, say, 6 people, there are 6 possible people that you could put in the first slot. So 6 possibilities overall for just 1. And what about the second slot? Well, you must have used up 1 person in order to fill the first slot, leaving 5 possibilities for the second slot. And if each possibility for the first slot, which there are 6, can branch out into more possibilities with the addition of the person in the second slot, of which there are 5, for which there are 5 possibilities, you multiply these two numbers to get the overall number of possibilities for filling those slots. So the next thing you do, naturally, is now that 2 people have filled the first 2 slots, there are 4 possible people with whom you can fill the third slot. And this chain of logical thinking continues all the way down until you're at the end. You have all these possibilities of filling up the first 5 slots. And for any possibility of the first 5 slots being filled, you know that you've used up 5 of your people, and there's only 1 possible person remaining that you could put in the final slot, i.e. 1 possibility. And that's why you get this sort of chain of multiplication. For instance, if we were doing this with 8 people, the same logic would apply, but it would be a chain of multiplication starting at 8. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And the simple mathematical way to write this kind of calculation, where you're taking some number and multiplying down by all of the numbers below it, is with that exclamation mark, or with that factorial function, hence the name n factorial. For instance, this number is 6 factorial or this number is 8 factorial. And that's sort of the most basic, at the most basic level, the first part of our solution. So now we know that how many ways, the number of ways in which we can sort 6 people into slots is 6 factorial, or this sum, or not really a sum, this product that multiplies out to 720. So that's for 6 people. Now, what now? You have 1 over root 2 to the power of n over 2. Where did I get this from? Well, as I say, it's about making sure that the order of people in pairs does not matter. So, for instance, in this situation of 6 people, you have 3 possible pairs. In a situation of 8, you would have 4 possible pairs, hence the n over 2. So 3 pairs here, 3 pairs here, 4 pairs here, because that's 6 over 2 and 8 over 2 respectively. But it still doesn't explain all this business with dividing by a factor of 2 for each pair. Well, that's because you need to consider that for every possible sequence that has a certain pair AB in a certain position, and it's just got some 4 other stuff, 4 other people here in some order, doesn't matter. For any sequence like this, there's going to be one corresponding sequence where the order is flipped, and these are all the same. But these 2 sequences must be talking about the same thing, right? So if we want to correct for the fact that the first pair could be flipped, giving 2 different possibilities for one configuration of the fan ships, then you'll want to divide by 2 to account for this double counting effect with respect to the first pair only. But the thing is, there are multiple pairs in this system. So if you want to look at the second pair, well then for each of these 2 possibilities, there are yet 2 more possibilities for the order of this second pair, all of which mean the same thing. So that means if you want to correct for how the order of the first and second pair does not matter, you'd need to divide by 4 because there are 4 possible ways to express that information. And this idea extends to the third pair, because for each of these 4 possibilities, there are yet 2 more possibilities for the writing of the third pair, i.e. what order it is in. And, for instance, if you have these 4 possibilities multiplied by 2, those 8 final possibilities for writing the configuration in these 3 pairs with the same order of pairs will be counted 8 times in this total sum, 720. So, we divide by a factor of 8, which is more helpfully expressed as 2 to the power of n over 2, because this fraction, n over 2, is the number of pairs for n people, where n is an even number. And to exponentiate 2 to this power means we're multiplying 2 by itself this many times to deal with the fact that there are that many pairs which could be reordered just by swapping the 2 members around. And for each reordering, there are only 2 possibilities, A before B or B before A. So overall, we multiply by this factor, 1 over 2 to the n over 2, for an even number, or in this case, divide by 8 to correct for that effect. Similarly, in a situation with 4 pairs, there are 16 possibilities if each pair stays where it is in terms of the order of the actual pairs, not just the members within the pairs. So for 8 people, we'd be dividing by 16. And that's why it generalizes to this 1 over 2 to the n over 2, because it's dependent on the number of people you're dealing with. And finally, we have this n over 2 factorial. So that might suggest to you that we are looking at an order of pairs because n over 2, as I established earlier, is the number of pairs involved in the system. And so why would we need to do that? Well, as I said earlier, this is to correct for another double counting effect. So for instance, we know we've already divided by 8 to deal with the fact that the members within the pairs might be ordered in several ways, leading to an overcounting of a single possibility of fanships. So dividing by 8, we get from 720 to just 90. But we divide by yet another factor, and the reason that is because say you have some unique configuration that you've worked out. Like suppose this is the only configuration you'll accept for a pairing of 1 and 2, 3 and 4, 5 and 6. Because you're trying to account for the fact that, say, in any given pair, there's an alternate way of ordering the members of the pair that creates a new possibility within this 720 sequences. In addition to this effect, you also need to consider the fact that the pairs themselves can be ordered in different ways. So, if you have this 1, 2, 3, 4, 5, 6, it's essentially the same as 3, 4, 1, 2, 5, 6, or 1, 2, 5, 6, 3, 4, 5, 6, 1, 2, 3, 4, and so on and so forth. And each of these orders of the pairs themselves has its own 8 possibilities to do with how the members within the pairs could be arranged. So 8 here, 8 here, 8 here, and 8 here. So clearly dividing by 8 is not adequate because it only gets us to overcounting in this way rather than in both this way and in the way that the members within the pairs might be ordered in different ways. Because it collapses 8 possibilities for each of these possibilities down to just 1. But we still need to deal with the fact that all of these possibilities mean the same thing when it comes to our fanship configuration. So, in essence, the number of possibilities that we're dealing with here is the number of ways you can order the pairs. And if there's n over 2 pairs, it must follow logically that there are n over 2 factorial ways in which you can order these pairs. So as you go down, n over 2 factorial, or 3 factorial, there's 3 possible pairs you could put in the first pair slot, multiplied by 2, i.e. you can choose either one of the remaining 2 pairs to put in the second pair slot, and the last one always goes in the final pair slot, leading to 3 times 2 times 1 is 6 possibilities for the ordering of pairs. So you must divide this number by another factor of 6 in order to account for this effect in the counting, such that you're only counting each fanship configuration once. So divide by 6, you get 15. For a 15-member boy or girl band, 15-member, 6-member boy or girl band where you're making the assumption that everyone must be paired off in a configuration, and the pairs are exclusive, you get 15 possibilities. And that's a surprisingly low number for me, like with my mathematical intuition, considering the fact that like there's actually no, that's not that mathematically low of a number. I don't know, I don't really know what to think about this, because this answer is actually, now that I think about it, this answer is really similar to an answer to another question in mathematics regarding a certain number of people. Like, and that question is, how many unique handshakes can you get between 2 people? So, but I know that the nature of the problem is not the same. So I'm thinking either this is an insane coincidence, or there's something deeper about this expression with n factorial 1 over 2 n over 2 and n over 2 factorial. Because if you have a group of 6 people, the total number of unique handshakes, or essentially possible single pairs, is also 15. But I personally suspect that this does not hold true as you move up to higher numbers. We'll just have to see. It's just an interesting mathematical coincidence. That's a bit of a side tangent. Now I'm going to get back to the original question at hand. So we've established that for even numbers, the number of people, or the number of possible fan chip configurations is n factorial over 2 to the n over 2 times n over 2 factorial. For even n. And how do we extend this to odd n? Well, we suppose that we have some number of, like, there's 7 people in BTS, for instance. You know that if everyone is paired up, you must exclude at least one person. And in this case, because we've made the assumption to simplify the situation that everyone, as far as possible, is in a pair, we are only excluding one person in any situation with an odd number. And the choice of who to exclude, well, there are 7 choices because there are 7 people. So if we say that F6 or Fn, the number of possible fan chip configurations, is this, then we know that if you exclude one person and find the number of possible configurations for fan chipping in the rest of the people, then you'd get the total number of configurations for excluding that one person. And of course, there's 7 people you could possibly exclude, meaning that, for instance, if you took a single member like Boy 1 from BTS, you excluded him, he's not in any pairing, but you still have the 15 possible combinations of pairings for the other people, then this leads to 15 configurations with the exclusion of one person. And then, for instance, if you exclude Boy 2, that's another 15 possible configurations, because the set of 6 members that you're creating these configurations for is different. So overall, for an odd number n, Fn is n times Fn minus 1 for odd n, where it's only explicitly defined for even n, because, well, like, obviously you could introduce that thing to the algebra, but it would be a little annoying because you'd have to write it out in a longer format. I think this whole expression evaluates to sort of n factorial over n minus 1 over 2 factorial 2 to the power of n minus 1 over 2, because that's the new number of pairings, n minus 1 over 2, rather than just n over 2. But anyways, those are the 2 formulae you could possibly use to deal with this situation. So let's go back to evaluating what we've learned in terms of the original problem. How many fan chip configurations are there for BTS? And I reiterate that this practice of fan shipping is like, it's kind of a screwed up thing to do. Like, these are real people. You can treat them as real people. You wouldn't do this to a group of your friends, for instance, unless you're kind of insane. But anyways, my personal views on the K-pop industry and this kind of fan activity aside, to answer the maths question, how many fan chip configurations are there for BTS? Well, we logically deduced that there must be 15 configurations for a group of 6 people, and we also deduced that there are this configuration is multiplied out 7 times when you add on the 7th person, because there are 7 possibilities of there are 7 possible ways in which you could choose one person to be excluded from the pairing up process. Meaning that overall, if you multiply by 7 to get the overall number of possibilities for a 7-member boy band, or girl band, or group of people in general, then you get 105 possibilities. So that's something to think about. If you have ever participated in this kind of thing, and you have like you have your own personal configuration of how the members in this band would be paired up. Well, I'm very sorry, but there's only 105 configurations. This band has hundreds of millions of followers. There are probably many people who thought up the same thing. But that does not mean to say that like the assumptions I've made detail the only possible way to describe the relationships between 7 people, because obviously we're assuming that they only come in pairs, and pairs are always exclusive. If you wanted to get more in-depth on this, well, I mean, like, this is the end of the video as far as answering the question in the thumbnail is concerned, but if you want to get a little more in-depth on this, you can try and think of ways in which you could describe the relationships between people. So, if you let some relationship be either sort of off or on, and a relationship is described as sort of like one person being attracted to or admiring or something along those lines, just sort of favoring another, then that means you have sort of one bit of information, 1, 0, or 1, that corresponds to whether the ordered pair, which is a mathematical term for some abstract thing where you have 2 objects and the order matters. For instance, boy 1, boy 2 is an ordered pair, which is unique and distinct from boy 2, boy 1. For each of these ordered lists of length 2, there is one corresponding possible relationship, one possible corresponding crush, liking, admiration, etc. that corresponds to this ordered pair. So if you have the number of ordered pairs in the band, each of which constitutes one sort of atomic, indivisible unit of human relationships, and like obviously human relationships are more complicated than this. This is just a really abstract mathematical model. Perhaps it is a meme gone too far, but anyways, if you have the number of these relationships, each of which is described by a single sort of bit of information, like whether it's there or not, nothing else about the more qualitative aspects of that kind of admiration that one person has for another, then you might say that there are, well, I mean, in BTS's case, 7 people. That means you have 7 possible starting elements of the list of 2, and 6 possible finishing elements of a list of 2, unless you are counting members' relationships with themselves, which I do not think we are, because we're looking at the social interactions between people. This leads us to 42 ordered pairs, or 42 possible admirations that might be held by one person of another in this group of 7, each of which can be a 0 or a 1, on or off, there or not. If this, like the sum of all of this information could be described in a 42-bit string, or 42-bit number, then, i.e. a sequence of 0s and 1s that we know somehow corresponds to the ordered lists, which each have one related sort of relationship between people, then the total number of social configurations you could fictionally dream up for this kind of 7-member band is 2 to the power of 42. And in general, just for completeness, it would be 2 to the power of n squared minus n, because you have n starting people multiplied by n minus 1 possible finishing people for an ordered list. And this number is about 4 trillion, just for reference. So maybe unique after all if you have thought of a configuration in these limits rather than the limits I described earlier when I was making a fairly idealized mathematical situation out of this whole thing. So that's all I have to say on this topic. I don't think, like, if you actually are interested in hearing me discuss what I think of the K-pop industry and what I think of fans of the K-pop industry, then do leave a comment or send me an email at watchmedomath@gmail.com. But this is a maths and physics YouTube channel. There is a good chance that my opinions won't be taken well. Or, I mean, like, I don't want to say that because it's just a really silly thing. It's just some form of entertainment that someone has opinions on. It's not really that relevant to what I do on this YouTube. But if you are interested, send me an email and we can discuss, or I can make a video about it. So until next time, thank you for watching. This has been Watch Me Do Math.